Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about the expected value of continuous random variables. To be more specific, we will present the definition of expected value for continuous random variables and show a few important results. Let's begin. Okay, first, that's the definition of expected value in the case of a continuous random variable. Can you see that it is extremely similar to the formula, to the definition that you had for the case of a discrete random variable? Back then, before, what we had was that the expected value of y, if y was discrete, was the summation for all possible values of y times the probability mass function, right? Okay, so now instead of a summation, right, instead of a sum, we have an integral from negative infinity to infinity of y times, instead of a PMF, a probability mass function, what we have is a PDF, a probability density function. Okay, so can you see that it is rather similar to the other one? Okay. So now let me show you a very important theorem. So now let g of y be a function of your original random variable, a transformation. Okay. Then if you want the expected value of a transformation of your original random variable y, all you have to do is modify the definition of expected value slightly. If you had y here, the expected value of y, we know, would be just the integral from negative infinity to infinity of y times the PDF. Okay? Well, if you have g of y, then you will have g of y here times the PDF. Okay? Now, again, let me remind you that you have seen a similar result in the case of discrete random variables. If I remember correctly, it was theorem 3.2. Anyway, what I want you to remember specifically is what we said. Hey, expected value of g of y, just before, when we had a discrete random variable, the summation for all y's of g of y times the PMF. Now something really similar. Hey, I want the expected value of g of y. No problem. Integral from negative infinity to infinity of g of y times the PDF. Okay, so same pattern. We are not going to be showing this result. Okay, but it's the proof would be very similar to the case, to the discrete case. Okay, so anyway, we're going to be using it, theorem 4.4, but we are not going to provide a proof. Okay. Okay. Now let me show you another theorem. So now what we have is several different transformations. G of y would be one of them, and then we have k transformations here. G1 of y, G2 of y, up to gk of y. Okay? Okay, so now what we would like to show is that the expected value of a constant is the constant itself. That the expected value of a constant times g of y, transformation of the original random variable is going to be just c times the expected value of that transformation, meaning we get to factor out that constant if you are dealing with an expected value, right? The other one, the expected value of a sum of transformations equals the sum of expected values. Make sense? And again, you have seen properties similar to these in the discrete case. Okay? We are going to show these. Okay? Going to provide a proof. So it's a theorem 4.5, right? Theorem 4.5 proof. So first, part A. Let me go back. What we want to show is that the expected value of a constant is the constant itself. Okay? So we want to show that the expected value of c, a constant, equals c. Okay. So first, this looks like the expected value of a something, a transformation, right? Which means that the one that we're going to be using is that theorem. Expected value of something, integral from negative infinity to infinity of the something times the PDF, right? Okay, so let's do that. By theorem 4.4, we have expected value of c will be, in this case, the case of a continuous random variable, will be the integral from negative infinity to infinity of c times the PDF of the random variable y. Make sense? Right? Okay. Now, by the linearity of integrals, we get to factor out that constant c. Let's do that. Now, in another video, remember that we said that legit probability density functions satisfy two conditions. One of them, f of y, is a non-negative function, meaning it's on or above the horizontal axis. The other one, that if you have a legit probability density function and you take the integral from negative infinity to infinity, that integral must be equal to 1. So that's what we have here. We have c times 1, which is going to help us conclude what we wanted, that the expected value of a constant is the constant itself. So that's the proof for part A. Not bad, right? It wasn't that hard. Okay, part B. We want to show that the expected value of c times g of y equals c times expected value of g of y. Let's do it. So we want to show that expected value of c times, let me write it down like this, c times g of y equals c times expected value of g of y. Okay. Proof. Again, expected value of something. Let's use theorem 4.4. Again, let me borrow that part. But now instead of c, we have something slightly more complicated. We have c times g evaluated at y. Okay, so now what we have is g of y here. Right? Then again we use the linearity of integrals, so we get to pull out that constant. And this is just the expected value of g of y, right? So c times expected value of g of y. So we're done. That's what we wanted to show. Done. Easy. Right? Now, let's see, I believe we wanted to show something else. Part C, third part. We wanted to show that the expected value of g1 at y plus g2 at y plus gk at y equals expected value of, well, the sum of expected values, right? Now let me do this for two functions of these, g1 of y and g2 of y. The proof is going to be the same if I had k terms in that sum instead of 2. Okay, you'll see. Okay, so we are going to show this for just two of them, g1 and g2. So the proof, as I said, will be similar if we had more terms in that sum, but I don't want to write too much, right? I don't want to spend too much time writing, okay? So again, guess what? We're going to be using theorem 4.4. No surprise there, right? So what we would have here is g1 evaluated at 1 plus g2 at y, okay, which means that here we will have g1 at y plus g2 at y times the PDF of our random variable y. Make sense? You agree? Okay. But now let's expand this, okay? This is the same as g1 at y times f at y g2 at y times f at y. You agree? Right? Next, note that by the linearity of integrals, we have the integral of a sum is the sum of integrals, right? So let me rewrite that integral like this. So it would be this guy here, the first one, plus the second one. And that's by the linearity of integrals, right? So we're not doing anything illegal here. But then note that this happens to be the expected value of G1 and this is the expected value of G2. So that's it. Expected value of G1 plus expected value of G2. And we are done. Note that if instead of two terms here we had k terms, then we would have g1 at y plus g2 at y plus dot 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 gk at y. We would have the same here, but we would have k terms. In that sum, we would use the linearity of integrals, and we would have the same conclusion, that the expected value of a sum is the sum of expected values. Okay? Great. Now, I would like to do an exercise with you that is going to be also useful. So we have a continuous random variable y with mean mu and variance sigma square. And we also have two constants a and b. Okay? So now what we would like to do is showing that the expected value of a times y plus b equals a times the expected value of y plus b. Okay? And then we want to show something similar, but in terms of the variance, that the variance of a times y plus b equals a squared times the variance of y. Okay, so we want the if we want to be more formal, what we want is the expected value of a linear transformation of our original random variable y. We want expected value and variance as well. Okay, let's do that one. Let me start here using a new one. Okay, so it's exercise 4.26. Exercise 4.26. Part A, we want to show that the expected value of a times y plus b equals a times expected value of y plus b. And we want to show that the variance of a times y plus b equals a squared the variance of y. Make sense? Okay, here we go. Proof. So we have the expected value of a sum, right? Okay, so expected value of a sum equals sum of expected values, right? So it would be just a times y plus expected value of b, right? So we know that from theorem 4.5, I believe. Let me check here. So theorem 4.5, let me see, where do we have that? Yeah, so from theorem 4.5 we have that the expected value of a sum is the sum of expected values, right? Okay. So that would be by theorem 4.5 part C or part 3, right? Okay. Now also there, because note that we want the expected value of a constant and we want the expected value of a times random variable. By part 2 we have expected value of a times y equals a times expected value of y, and by part 1 we have expected value of a constant, the constant itself. So let me just copy and paste and then just say that by the other two parts we have what we want. By theorem 4.5 parts 2 and 1, right? Parts 2 and 1, and we're done. We have shown the first part. Okay, now let's show the second part. Okay, but to make it very clear, let me introduce this notation here. Let W be that transformation that I want. Okay, a times y plus b. Now note that the expected value of W is going to be what? Oh, it's going to be the expected value of a times y plus b, right? But from part A we know that the expected value of W will be a times expected value of y plus b. And we could say that. Let me write it down here. From part A. Okay? Okay. So anyway, note that what we want is the variance of a times y plus b, which is the variance of my random variable W, right? So variance of W, by definition, the variance of W is the expected value of W minus its expected value, the whole thing squared, right? That's the definition of variance, right? By definition. Now let me plug in what we have. W was defined like this, a times y plus b. So w is a times y plus b. And then I'm going to need curly brackets here, because I'm going to need some square brackets here. Okay. Now let me rewrite the expected value. Expected value is this. So I have minus the expected value of w, which happens to be this. Right? So just plugging in what w is, a times y plus b, and then just I'm going to substitute the expression in terms of y for the expected value of w, a times expected value of y plus b. Right? Okay. Now let me expand this and try and simplify that. So that's the same as minus times a expected value of y minus b, right? And then we have the whole thing squared, right? Let me remove these brackets, right? Make sense? So note that plus b minus b, those two guys will cancel out, so the only thing that we have left, well, the only two terms that we have left are a times y minus a times expected value of y. Okay? So let me get rid of those b's. There, there. Okay? Okay. Now, these a's are the same, right? A and A. Let me change here to make it look clearer. Okay. A. Okay, that's better. Okay. Anyway, as I was saying, we could factor out that A so that's the same as this. This would be the same as a times y. This would be the same as a times minus expected value of y. Right? And we still have that squared. So when we square this, a times y minus expected value of y, that would be the same as this. A squared a squared times expected, well, times y minus expected value of y, the whole thing squared. Make sense? Yeah? But now, this is the expected value of a constant times something. I get to factor out that constant. Let me factor out that a squared. And then we have that expected value without the a squared. Take a close look at that expected value. That expected value is by definition the variance of y, right? So this is a squared times the variance of the random variable y. So what we have shown is that the expected value of a times y plus b equals a squared times the variance of y. Or in other words, the variance of a constant is 0, and when we have a times y and a is a constant, right? What you have to do if you want to factor it out, you have to square it if you're dealing with the variance. Okay? Well, so that's it for now. These are the results that I wanted to show with you. Okay, so we're done. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.